Hi everyone, Mike here, and we're going to do some examples of using the CLT, the central limit theorem. Here's the classic type of CLT problem. Suppose the mean time for an oil change at 10-minute oil change is 11.4 minutes. They're giving you mu there, with a standard deviation of 3.2 minutes. They're giving you population quantities. If a random sample of 35, now it's over 30, so CLT kicks in, what's the probability that the mean oil change time is less than 11 minutes? So we're looking for the probability of X bar being less than 11. Now, again, you could not answer this question. The probability X is less than 11 because you don't know anything about X. You know the mean of X, you know the standard deviation of X. You don't know the distribution of X. So because of that, you cannot answer that question. Because of CLT, you can answer a question about X bar. So we want to find the probability X bar is less than 11 by the central limit theorem. X bar is normally distributed around the true population mean mu and standard deviation sigma over root n. That's what we have here. So the answer is simply, we're going to find the probability X bar is less than 11 using the p-norm command in R. And you very quickly and easily get the answer. That's the CLT. Another example of the CLT is the service time for customers coming through a checkout counter in a store are random variables with a mean of 1.5 minutes, that's mu again, and a variance of 1, that's sigma squared. If sigma squared is 1, sigma's 1, you know that. What's the probability that 88 customers can be serviced in less than 2 hours of total service time by this one checkout counter? Sounds a little bit different. What's the probability that 88 customers can be serviced? Well, you want to find the probability the sum of the 88 times is less than 120 minutes. That's 2 hours. If we divide both sides by 88, which is n in this case, we obtain the probability X bar is less than 1.36. That's a CLT. CLT kicks in. CLT. From the central limit theorem, we know X bar is normally distributed on the true mean mu with standard deviation sigma over root n, and then we're good to go. The probability X bar is less than 1.36. You could z-score it, which we do here, or you could go and use the p-norm command in R, exact same thing. You'll get the same answer, around 10%, just a little under 10%. So there's about a 10% chance 88 customers can be serviced within 2 hours total. Again, central limit theorem is a nice device that lets you answer probability questions about the sample mean X bar. How large is large enough for the CLT to kick in? Usually n bigger than 30 is what we say. That's the party line. If the underlying population is not too skewed, if it's more symmetric, n's bigger than 15. If the underlying population is normal, this works for any sample size. N equals 2, n equals 3, it does not matter. But in general, we say if we don't know anything about the underlying population, n bigger than 30, the CLT should kick in. Summary about the central limit theorem then is you have a random variable x from an unknown distribution. We know the mean and we know the standard deviation. We don't know what the distribution is, doesn't matter. It can be discrete or it can be continuous, doesn't matter. You take a sample size, you take sample 1, you take a sample 2, you take a sample 3, say, I don't know why we have n equals 60, but of any size as long as it's bigger than 30. Take many samples. If you looked at a histogram of these X bars from many different samples, it would look like a bell-shaped curve. Technically, what happens is X bar is normally distributed, centered around the true population mean mu, with standard deviation given by sigma over root n. The theoretical result. How we actually use it, you'll have to wait till next video when we do confidence intervals. Thank you and hope you're having a great day.